Cool. Okay. Hi, everybody. I'm Scott Mansfield. I'm a senior software engineer on the EVCache team at Netflix. We're going to go through a bunch of stuff. This is kind of the theme of the night, it seems. This is not specifically about Go as a language, but it is about how we use Go in our larger products like ecosystem and what my team does. What is it? It's ephemeral volatile cache. So it's our Netflix like online cloud-based services caching tier. It's clustered memcached. We run on AWS, so it's tuned for AWS and specifically Netflix use cases on AWS. It's distributed, sharded, replicated, all the buzzwords. It has tunable replication both inside one region and across the entire globe, where we operate out of 3 regions. It's highly resilient to failure. One of my coworkers recently gave a talk and called AWS Chaos Monkey as a service, which is about right. They kill more of our boxes than Chaos Monkey does. We're also topologically aware, mostly for speed purposes. We'll try a closer box first. We have a data chunking feature for large objects in memcached, and there's some other extra functionality on top of that that I'll go into later. So this is an output of our request tracing system. And this is a typical homepage request. So if you look, we had a request come in and stands out to a bunch of different things. On the far edge, the right edge of all of that, there's maybe half a dozen that are not an EVCache box. So we're hit pretty heavily on a regular basis for seemingly normal requests. We might get hit 3 or 4 dozen times. So AWS, in case some of you don't know, is a pretty volatile environment. So instances will just up and disappear, or they might get degraded in a variety of different ways, which is more fun. An AZ, an entire availability zone, can disappear, or regions can disappear. That actually happened recently. There was an AWS network outage yesterday, in US East 1, and we evacuated all traffic. And so we exercise this on a monthly basis at least, so we're pretty used to it. The network itself actually can be lossy, and we see customers kind of ping pong between regions. So there's all these different ways that people kind of screw with us. So just to give you a sense of scale for us, there's 70 clusters. You guys can read all the numbers. I wanted to point out that we're in the tens of millions ops per second, trillions of requests per day to our caches. We run a little over 11,000 servers. Okay. So basic architecture, if you're just looking at one, let me do this way because people on the stream can't see the pointer. So this is like our server, like a single server, or sorry, this is our single client. This is our single server over here. And then we have a service discovery system at Netflix called EVCache. So the server, when it starts up, there's memcached. Prana will poke Eureka and say, hey, I'm up, I'm registering. The client will pull lists of servers and make connections directly to memcached over here. So the architecture between client and servers, it's a complete bipartite graph. I didn't actually know the name for it for a while, but all clients are connected to all servers, so it's kind of a full mesh between the 2 sides. In brief, the sets fan out and it gets preferred closer servers. We'll look at that in a second. There's actually multiple full copies of data. So you see, like in one availability zone over here, there's actually a full copy of our data, and then another one in US West 2B and another one in US West 2C. So for reading, basic operations here, reading, you try local servers first. You try topologically closer servers. So in this case, we have like 3 copies of data. We have many clients across the whole region, and the one in US West 2A is normally fine, but say this server over here just up and dies for some reason, we have 2 other backups. So we have this one and we have that one, and it can try reading from either one of those or both to try and get data even if that server's done. So writing, like I said earlier, it fans out. So in this case, if you want to write to the first server, it would write to all 3 at the same time. So first use case that I'm going to look at is a look-aside cache. So this is your kind of classical cache. You have something in front of something else slower. So we would first try and look for something in the cache. If it's not there, you can go to the service that owns that data, which will then go to its database and then write back into the cache and then return the data so that next time you want to go look at it, the data is actually there and it'll be a lot faster. Here's a much more interesting case for us. So we are actually the primary storage mechanism for our personalization algorithm output. So everybody's profile every single day for every device that you've been looking at recently has a new homepage generated for it. Overnight, there's really large-scale pre-compute, and it's not just in like one stage, there's multiple different stages to it. So each one of those is actually overnight is writing into the cache. It's dumping, most of them have terabytes of data per stage. So we have a bunch of data going into the cache. And then real-time traffic is just reading directly from the cache. There's really no service or anything that does this live because generating a homepage takes like, I don't know how many compute seconds, like 15. You can't do it while you're waiting. So we have fallbacks in that case. So the overall thing kind of looks like this. We have our online services and the offline services kind of separated by an EVCache cluster. And that's basically our buffer. This is a pretty standard one, think session storage. So when you're watching a video, you are pinging every minute or so. You're sending back a bookmark that says, hey, I'm at this point, I'm at this point, I'm at this point. So it's just constantly updating an EVCache cluster. Right, so there's a bunch of other things that we do on top of this as a team. We do, well, I won't read it out to you, but we have a Kafka cluster that we send mutation metadata to. So what that means is we can do a bunch of different things on top of that. We have our data replication, which I'll show you in just a second, and we have secondary indexing for point queries in case somebody wants to figure out if something went wrong, and cache forming, which we'll also look at, and we also have a consistency checker that can run off of this metadata and just run while data is being written and make sure that everything's fine. So say region A and region B, we actually have 3 regions, so this counts between all pairs. You do something, you set a key, it sends some metadata to Kafka. We have a system that we call a replication relay that is pulling, is listening to this Kafka metadata stream. And it'll pull the data if it needs to and send it across the wire to the other region, so also our own system. It will proxy that to the local EVCache cluster there, and then the app, whenever it needs to, can read that data. And this is, like I said, a full mesh between all 3 regions, so this goes in every which way. It also, so I say get data for set, but if we do like deletes and stuff like that, or we can actually invalidate caches in other regions, it's pretty configurable for us. So if you're running and you're in your normal happy mode, but we need to deploy a new version of our software, we do have a cache warmer. So instead of waiting for the TTL to run out and all new data to be written to all copies, we bring up a new one that's kind of empty. We pull this cache warmer, we bring up a cache warmer service. We'll pull the data from the old one, write it to the new one, and when the new one looks like the old one, we can tear everything down, and then we're running in our steady state again with the new software. So all this is hidden behind a very simple API for our customers inside Netflix. So they just build a new EVCache client. They can do set, get, touch, delete, whatever. And all of that detail that I've just shown you is hidden behind that API for them. Okay, so there's a bunch of things that are actually in our client. Our client has a lot of smarts in it, which might be going against a lot of the servers should be smart, clients should be dumb kind of thing. But it's working out for us really well so far. We have fast failure in case queues get full, or we know a box is bad. We have tunable read retries. We can try many times. We can wait it longer. We can do whatever we need with that. There's queues for bursty traffic. And one recent development was a latch. So we have like 2 out of 3 copies, or n over 2 plus 1, or n minus 1, or n. We can wait on a certain number of boxes to actually receive that right before we move on. And of course, the Kafka replication stream is async. So when somebody's writing at a high rate, they're not waiting for it to be in Kafka before they continue on. And this is fine for us because it's reliable enough that we don't have to worry about that. Okay, so this is like the second part. That was all kind of like our world view. So this is a talk about Moneta, which is our current project that I've been working on we've been working on for 8 months. And I call this also, i.e. why I'm talking about this at a Go meetup, because this has kind of not been Go-centric so far. So we have a project called Moneta. It's named after the goddess of memory, which is kind of what we are in Netflix, and the protectors of funds for Juno. It's an evolution of our server. So if you saw earlier, the server before was just memcached and our Prana sidecar. And now we can use the SSD on those boxes to store cold data. So for us, this is really cost optimization. And we track internally like cost per stream. It's a metric that's kind of important to us. We're trying to make sure that stays in check. And this is actually going to lower our team's cost per stream now, and on an ongoing basis, our increase will be basically lower. So this is a big win for us. So, right, you've seen this before. The old server is just memcached Prana. Prana is our Java sidecar. It's also open source. It's just our hook into the rest of the Netflix ecosystem. All it does is the service discovery that you saw earlier and then metrics reporting. But so this worked for a long time, 6, 7 years. That was really great, but the end of last year, we moved to an N+1 architecture with 3 regions. So we had to start replicating that data that was normally like either in an island in EU or just not really copied everywhere to everywhere. That was a pretty big cost increase. And we also, at the beginning of this year, launched in 130 new countries at the same time, which was fun, but it's also a lot more data. And that data is also replicated everywhere. So it started to get a lot more expensive really quick. The other thing to note for us, though, is that our access patterns are very heavily region-oriented. If you're sitting in California on your PS4 watching Netflix, you're going to be hitting US West 2 99.99, I don't know exactly where it is, but it's almost always. And that means the hot data in one region is cold data in other regions. Some data is just cold all the time. So what we're going to do now, and actually what we're rolling out now, is hot data in RAM, cold data on disk, and it also affects our scaling, but that's fine. And the new server looks like this. So we have a proxy in front we call rend, and then this other piece here called mnemonic. So in this case, rend is a proxy here. It doesn't really store any information. Memcached acts as our L1 cache, and then mnemonic is our L2 cache. We also still have Prana and other stuff running on the box that are kind of insignificant. So for us, this is really great because if you notice, the client isn't in this picture. The client is actually exactly the same as it was before. And we now have code that we own running on the server. We don't actually touch memcached, so it's still stock memcached. And that allows us to both do this L1, L2, and also any server-side intelligence that we actually want to add in the future. So I'll talk about rend first, and then I'll talk about mnemonic. So rend is already open source. It has been since the first line of code, actually, which is an experiment for Netflix, but it was fun. You can also it's go gettable and everything. So it's our high performance memcached proxy and server. So it's written in Go. This is the part that matters to you guys. It mostly for patterns like one Go routine per connection kind of thing. And it's also pretty easy to pick up, and it's fast when it runs. We're very latency sensitive. Kind of putting anything in front of memcached ends up slowing it down because memcached is just so fast. It has tons of years of optimization work put into it. So you weren't going to run Java, for example, in front of it. It manages that L1, L2 relationship between memcached and mnemonic in the same box. It does that data chunking feature I talked about earlier. It was in the client, and now it's implemented on the server side. And that actually did some operations for like 30x faster because of that. Doing it from a distance is a lot harder than doing it locally. And our starting requirements include tens of thousands of concurrent connections. We have some caches with 20K right now. And those are normally on memcached. Now we have to deal with it in rend. So this is more detail about what the project actually looks like. So it's actually a set of libraries. This is important for us for reasons that will become apparent in a minute. There's connection management, the server loop, the protocol parsing from memcached, request orchestration between L1 and L2, and then the actual pieces that speak to the backing storage mechanisms. It also includes our own homegrown metrics library, which might make some people cringe, but it worked out pretty well for us. we can make it do whatever we need to. For example, our histograms have to match the buckets that our metrics system internally chose. So we can't modify an open source one to do that. We're just going to have our own. It also includes actually a feature called parallel locking for data integrity, but what that really means is any one key can't have two operations at the same time. So this helps us maintain consistency between L1 and L2, but it also allows up to however many parallel requests that you want. So, right. What it actually looks like in production, I'll talk about mnemonic in a second, but what it actually looks like in production right now, it's serving some of our, actually I think it literally is the most important personalization data that we have, is already running on this. So we've seen some good wins with it. We run with 2 separate ports, and this is an optimization for our batch compute systems that we have running. So every night we're doing all those really big batch computes. If we just dump that into a system like this where now L1 is just the visiting traffic, we would blow away our L1 and everybody would be getting disk reads. So we have a way now to separate those kinds of different traffic to write into L2 and replace an L1 instead of just blowing away our cache. Okay, so mnemonic will be open source soon, sometime soon. I'm hoping by the end of this year, but that's not a promise. Anyway, it reuses a lot of the Ren code. So this is the important part. This is why I said it's important that it's broken up into a bunch of libraries, because it's using that here. But then there's another handler in the back end that actually is just a thin wrapper around this C++ library, which is using RocksDB underneath to do the actual storage on disk. So I know this is a break from what other people have done in the Go community, where they tend to interact with RocksDB at a very low level. For us, that was not a good use of our time because we had a person on our team who was good at C++. So we have a C++ library that exposes a very simple C API instead of working with RocksDB at a very low level. Right. So it basically just does all the normal memcached operations into RocksDB. So why? It's pretty fast for us. Our latency read goal was 20 milliseconds. That's our default timeout, so we want to try and stay below that. And it's really good at writing lots of data fast. So this is, again, we have batch pre-computes writing a whole ton of data into our caches every night. We want to have the ability to write pretty fast. This is a picture of some of the internals, but essentially it will write into memory and then flush to disk asynchronously, and those files will be immutable from then on. We use it in a FIFO compaction. I have quotes because it's not really compacting anything. It's essentially first in, first out, first file that was written will get pushed out the end. And we try to make sure that things stay fast by pinning certain important bits in memory. So like our misses have to run down the entire file list will stay consistently fast. And we also, in order to limit that latency, we also shard across many RocksDB instances. So there's a few dozen actual separate databases, and then that C++ library does this sharding and separation between them. So this is actually, it's good for us, for people who are looking at this and going, oh, that sounds like a really great idea. It's really not that good if you have a single record that's updating 50 million times in a row, because it can push out valid data. So for us, because we have those batch pre-computes, again, this is still optimized for Netflix. We have those batch pre-computes that can, we can size the disk so that we won't push out valid data. And we might work on this. It's kind of a hard problem. Most people just kind of run with the normal default compaction, and we're not entirely sure where we're going to go with that yet. So we did a test, 1,000 writes per second, 3,000 reads per second, and we had a forced 10% miss rate, and we had a 99th percentile latency of 1.7 milliseconds. So for us, this is really great. We use I2X larges for this, so they're high I/O into the disk. The network is the same as the previous instance type that we were using, R3s. And we actually have, production data, like real world data, that thing that I talked about, the most important personalization bit. The traffic to that is about half a millisecond average, and I believe 95th is 2 milliseconds and 99th is 3 or 3.5 milliseconds right now. So this is great for us. This worked out really well. Two pieces of this, the EVCache client library in Java, and then Rend, our proxy, our open source. The mnemonic piece, like I said, is soon. And I think that's all I have. Yeah, you can see my Twitter handle. I have to look at them on my screen?
Yeah, I can't see all of them.
Uh-oh. Okay.
Let me see uploaded on. Are there any questions in the audience? Cindy?
You talk about a metrics library that you use that was like built in-house. I was wondering if that's just a library or if it uses like any popular system math backend.
No, so what the metrics library does is just collect metrics, right, and then it has a HTTP endpoint on box. Our Prana sidecar is polling that endpoint every minute or so to pull metrics out.
Okay, cool.
Yeah, Brad?
You had a bullet that said the miss rate was 10% rather than the hit rate was 90%. That's like you're more of a glass with half empty sort of guy.
Okay, so I just realized when you were asking your question, I forgot to repeat yours, Cindy. You were talking about what backend we were using for metrics, so that's what that question was. The next question was, is the glass half full or half empty? The reason I said that is because a lot of the time our hit rates are kind of absurdly high, like 99.5% or something like that. So this was a worst case scenario for us. That's why we're testing it at a 90% hit rate, 10% miss rate. Yes?
I think I understood you to say that the addition of Rend to the client and EVCache was transparent to the client, like the writing side was still the same. So where do you determine which goes into hot storage and which goes into cold storage?
Yeah, good question. So the question was the Rend is transparent, so how do we pick what goes into hot and what goes into cold? Right, so Rend is transparent. It looks exactly like memcache to an observer. And depending on which port you write to, that's where that standard and batch port stuff came in. So let me get back to that second point too. So this the standard port and the batch port have different behavior based on who's writing. So for our standard port, we would write into both. And for the batch one, we would write onto disk first, and then we check like if there's anything in L1 that's currently being used, we would replace it. Otherwise, we just don't touch it. And from there, memcache has a pretty good LRU algorithm, and we just let that take over and evict things that have not been used recently. Yeah. Sorry, let me. There's been a few here. Let me see if there's one on here. Yes. Okay, so. It's talking about the personalization, how I talked about the, we generate a new homepage every night, and what do we do about new users? Kind of outside the scope for the talk, but we have good fallbacks, basically. And the first time you visit, we actually have a near-line compute system that I didn't show. So when you visit and your homepage isn't there, we'll fire off a message and it'll get computed, but you won't get that right away. You'll get it the next time you look at the homepage. Okay. And will the slides be available? Yes, I'll make the slides available. Okay. Yes.
Maybe I missed it, but how are the clients talking to? And the other one is, are they talking exclusively to EVCache or is this from other sources?
Okay, so question one: how are they talking to EVCache? We vend we vend a Java client library. So in all of these images, we have our clients here, and that's our client library. We vend a jar, basically. No, it's a memcache protocol. We actually use the binary memcache protocol. Yeah. And then the second question.
Are they talking exclusively?
Do they talk exclusively to EVCache? No. So they can do whatever they feel like outside of EVCache. We don't do that. We talk to our own servers. But for people in this kind of pattern, they would also talk to the service. But for people in other kinds of patterns like this one or this one, they don't. They'll just talk to the EVCache. Yes, pink shirt.
Is the client shard aware?
Yes, the client is shard aware. So that's when you're looking at like this, it'll actually know like this is a full copy of data here, and then like other full copies of data in other places. When you request a key, it'll try the local one first, and it will shard and pick the right server. There's no intermediary. Yes.
So you mentioned you use RocksDB. I was just curious if there was like any particular design decisions for choosing that as a local key value, so some of the alternatives.
Generally speed. I was not the engineer who did the majority of research on that. He's actually not here tonight. So, sorry, yes. The question was why RocksDB for the disk back storage. It's got a pretty large user base, which is nice for us. It's fast enough, and it's configurable to the point where we can use it in the way that we want. You can turn off compaction, basically, is what's nice about it. But there's a few other things that we can talk about it after the talk, too, if you want. We can go into more detail. Yes?
What drove the decision to the oxidate? So how much research you did on that?
Okay. So why the instance type? So we currently, in our old server, we use R3s, R3 large XL, 2XL. Anything bigger than that, we consider it to have too much data on it, so we can't let one instance have like a fifth of our data set. It'd be kind of absurd if it just disappeared. That's because of the high memory data type. I2s are basically basically R3s, but with more disk attached. So we're using that because it's what we're very familiar with, but it has the disk space that we need. R3s have a very tiny disk.
Okay.
Do we have one more? He said his hand up.
One more.
Okay.
Talk about interesting failure modes using and how you found them, how you
Oh, for hours. The question is, are there any interesting failure modes that we've seen? And yes, and I don't want to take up 3 hours of time, so I will talk to you about that after.
Okay, then the one over there, go ahead.
So, how do you maintain the consistency between the SSD and the cache? Unless, given that each one can fail independently, how are you using it to fix it?
Okay, how do we maintain consistency between L1 and L2? For caches where we strictly need that, we use the locking feature that it talks about, where no one operation can happen on both, happen on the same key at the same time. You can't have two operations happening on the same key at the same time. So
each operation can fail independently.
Yeah, so if the operation fails, we generally fail the overall operation. So if it's like a set, we allow somebody to redo that. In general, our philosophy is not to program for the millions of corner cases. We solve the vast majority with much simpler code. And because we are not a durable storage mechanism, we don't generally have to worry about the millions of corner cases. It's a philosophy question. So, yeah. Okay, I think that's it.